In this problem, we want to find the forces on both tugboats T1 and T2 in terms of variables A, M, D, and R. And in this case, it's not an equilibrium, so there will be an acceleration. Let's go ahead and use Newton's second law again. So this is the main equation. The sum of all forces is equal to mass times the acceleration. So it's a two-dimensional problem since the tugboats are not going perfectly in line with the main cruise ship. It's going off to the sides. We're going to have to look at first the X component and the Y component. Given the problem, we could already see that the ship is not going to go in the case of looking at the picture left and right, it's only going to go forward, right? So there is no acceleration in the y-axis given the two-dimensional plane of the picture. So then MAY will equal to 0. Now A of x is actually going to be what the picture or the problem defined as just A. So we're going to just call it whatever the problem gave you as a variable and just say it's A, because that's the actual acceleration of the cruise ship. Okay, let's go ahead and list all the forces in the X direction first, and then we'll just do the Y direction as needed. You have two tugboats. We have the D, which is the force of the ship's motor, and then we have R, which is the resistance due to the water. So that's kind of what the labels are giving you, is that T1 and T2 are the tugboats. We have D, which is the ship's motor. And then we have R, which is the water resistance. Okay, and then these two are the tugboats. And these are all forces, right? So here are the four forces you have. Let's go ahead and list them all as their X components are dictated. So we have tugboat 1 cosine of 30 degrees, and it's going to be in the positive direction, plus tugboat 2 cosine of 30 degrees, positive direction, plus D minus R is equal to MA. And again, we're going to continue using the conventional system for positive values up and to the right. Okay, so what do we know? We need to actually know T1 and T2. We know D, we know R, we know M, and we know A apparently. So this is a good equation. It helps a little bit, but we don't know the connection between T1 and T2. So now we're going to do a little side quest. This actually ends up being a little side quest where we look at the Y component. The Y component is consisting only of two forces because D and R only goes to the right and to the left with respect to the picture. So T1 goes up, T2 goes down. We're going to go ahead and say T1 sine 30 degrees minus T2 sine 30 degrees is equal to 0. We cancel out the sine 30s because if you divide both sides by sine 30, this 0 divided by sine 30 still remains 0. So now we end up saying that tugboat T1 is equal to tugboat T2, and that is our relationship between the two tugboats. So now that we know that, we can say that both tugboats, T1, T2, are now just T. So they're both pulling with the exact same force, and we'll call it T. Now, if we're going to solve for the forces on the tugboats T, each tugboat T, we can go ahead and use this equation, but now we can just call T1 and T2 simply T. So we have T cosine 30 plus T cosine 30 plus D minus R is equal to M times A. This ends up being, if you were to isolate T, this is 2T cosine 30. And we'll go ahead and start dragging R and D on the other side. It's going to be equal to MA plus R minus D. Now isolating T, we have to divide both sides by 2 cosine 30. And we end up getting T equaling to MA plus R minus D divided by 2 cosine 30. If you want to do one more calculation, you'll see that cosine 30 is root 3 over 2. So if you multiply that by 2, this problem then becomes ma plus r minus d, but divided by root 3, and that might look a little prettier. That is the force of each tugboat acting on the cruise ship in order to make it accelerate at a rate of a.